Kartik, welcome to the Instituto Astronomía and our virtual Coloquio.
Great, thank you.
I give the floor to our moderator, Nisim. It's a pleasure to have you here.
Okay, go ahead, Kartik.
Thank you. So I hope you can hear me, and in case my internet connection cuts down, which it often is just inconsistent, I'll come back to it. And I'm really pleased to share with you some of the scientific research that I've done in my career, but I'm happy to answer questions on any of the things Jillian mentioned on my work at NASA headquarters. Now that I'm on the agency government side, I still do a lot of research, primarily actively with ALMA and the Cosmos Consortium. And the results I'm going to show you today primarily come from the work that I did with the Cosmos collaboration. And I hope that by the end of this 45 minutes or so, I can convince you that with this work, we have really figured out the rate at which galaxy disks came into existence over cosmic time. We haven't fully finished analyzing this, but with James Webb, we will have the opportunity to do it all the way to the beginning of the first galaxy disks. So, a typical colloquium looks like this, where in about 10 or 15 minutes, your understanding of what I'm talking about is going to go down below 50%. I live in Washington, D.C., and my goal is not to talk like a politician. And this is the ideal goal. So if for whatever reason, you feel that I'm losing you, especially in this virtual world, I don't mind being interrupted. Just unmute yourself and interrupt me and just say, hey, can you go back? I missed that, whatever. So that would be fine. The work that I'm presenting here is done with a large group of people. And because we're trying to piece together the history of the evolution of galaxies, kind of divided up into the high redshift universe and cosmological evolution, the local universe work. Those are the two things I'll present to you. I won't get a chance to talk about the work I've done with Magellanics and late type galaxies, where all the action is today, but happy again to answer those questions if you're interested. The color coding is just showing people who worked with me as postdocs, or in yellow as graduate students, postdocs in orange, graduate students in yellow, and undergraduates in green. And Diana Powell actually is now a graduate student about to graduate as well. So I like starting with this slide, which is from the 1990s that Alan Dressler and his team put together in the previous astrophysics roadmap for NASA. The last one that we did that I would like to just advertise to you is called Enduring Quest, Daring Visions. And I was one of the people on the team who put that one together, which lays out the NASA vision for the next 30 or 50 years. But this slide actually comes from the one before. And I like this slide because it pieces together the jigsaw puzzle that all of us as scientists, whether we're chemists or biologists or geologists or astronomers, are trying to put together. It's the jigsaw puzzle of our origins. Where did we come from and how did we end up here? My research is primarily targeted at trying to understand the formation and evolution of galaxies, the fundamental building blocks of our universe. A good place to start if you're trying to understand how the first galaxies came about and why the universe looks like the way it does might be to start in the local neighborhood and say, well, what do galaxies look like around us? And in 1927, Hubble published a paper where he first submitted the Hubble tuning fork. Ellipticals are on the left, and as you all know, as you go to the right, you see the disk galaxies. And typically, we divide them into two branches. On the top, going from S0s, which we typically call early type galaxies, all the way to the right, which are late type galaxies. We're going from galaxies that have a large bulge to galaxies that have smaller bulges, and going from galaxies that have tightly wound spiral arms to galaxies that don't have tightly wound spiral arms. Hubble called the top part of this tuning fork diagram right here the normal galaxies. And he called these galaxies, barred galaxies. But as I'll show you, the barred galaxies, in fact, are the most common type of galaxies, and in fact are the quote unquote normal galaxies of today. And what we want to try to figure out is what happened as you go back in the past. And I'll try to convince you that bars and stellar bars are extremely important signposts of the evolution of the state and the maturity of a galaxy disk. So when bars were discovered, I mean, it goes back to 1872 when the Earl of Rosse in Ireland actually first identified a barred galaxy. But in the 60s, de Vauclair's classified galaxies in the local universe and saw that 2/3 of all local disk galaxies had a bar in them. And the question was, why was that the case? And the first simulation, so this is, I think, a 10,000 particle simulation by Hole in 1971, they found that in this n-body simulation, the disk wasn't stable, that just in a few rotational timescale, the disk would collapse and form a bar in the center. Kalnas called it a troublesome mode. And there was a very important seminal paper in 1973 by Oestreicher and Peebles, who concluded that bars were inevitable in galaxy disks once galaxy disks had achieved certain conditions. When a galaxy disk was isolated, it was massive, it was primarily supported by rotational motions, and was dynamically cold. In other words, things weren't moving up and down, but were primarily in this flat disk. Then in those kinds of galaxy disks, bars were inevitable and they must form. But at that time, they knew that in 1/3 of the galaxies, there were no bars present. So they then decided in that paper that something must be keeping those bars from forming. And they argued that it must be the dark matter that is stabilizing the bars against forming in those galaxies. They were partly correct. It turns out that with better simulations where you allow the dark matter halo particles to interact gravitationally with the baryonic matter, even in galaxy disks that are originally dominated by dark matter, bars do form. And the bars that form in galaxies that originally are dominated by dark matter end up in fact being bars that are stronger, leaner, and meaner than bars that would have formed without a dark matter dominant halo at the beginning. And the reason for this is very, very simple. The way to think about bar formation is that the formation of a stellar bar is the lowest energy state for the stars to be in at the center of a disk. And in order for those stars to form a bar, this very stable state, they have to give up angular momentum and energy to something. And typically they give off angular momentum and energy to either stars in the outer disk or to the dark matter halo. So when you have two sinks of energy and angular momentum in the outer disk and the dark matter halo, then the bar tends to be stronger, leaner, and meaner. And so the way to think about bars is that bars are really the ultimate endpoint in the maturity of a galaxy disk. And as a galaxy disk forms and becomes an adult disk, it ought to form a bar. And the question of why 1/3 of the galaxies today are unbarred is an interesting question, and we can talk about that at the end of the talk. But primarily what we can think about bars as a signpost, as a maturity state of a galaxy disk. And we want to use that to try to understand the state of disks as we go back in cosmic time. And so we want to use the presence or absence of bars as a function of look back time, as evidence of how disks are evolving over time. Now, mergers and interactions throw a monkey wrench in this, and I'm going to skip discussion on that, but happy to answer that question later on. So the question we want to ask is, how does the bar fraction vary with redshift as we go back in time? And the first results at high redshift, and by high, I mean actually very low redshift, only at redshift of 0.5 or so. On the right-hand side was the Hubble Deep Field work that Bob Abraham and Richard Ellis and Sidney Vandenberg and their team had done. And the first paper by Vandenberg et al. And then by Abraham et al. Said, oh, there's basically no bars present beyond a redshift of 0.5. Now, the identification techniques for bars was somewhat immature. In the Vandenberg paper, they really did it only visual classification. But in spite of that, this suggestion was really revolutionary at the time because it suggested that something was very different with galaxy disks only 4 or 5 billion years ago. And so the possibilities were either galaxy disks were dynamically too hot, either they were not massive enough, or there were too many mergers and interactions going on that heated up the disk, or something was different. And so if that was true, it was putting a strong constraint on the evolution and assembly of galaxy disks. So this was the state of the art in 1996, 1999. Then when I went to Caltech as a postdoctoral fellow after finishing my PhD at Maryland in 2001, I thought, well, as you look back in time, you're really looking at bluer and bluer systems. So maybe Bob and Sydney and those, they actually missed some bars because they were looking at rest frame blue light where bars are harder to see because bars are primarily a stellar structure. So what we did was we did a study with the NICMOS Hubble Deep Field. And what we found was there was no compelling evidence for an absence of bars greater than redshift of 0.7. However, there's a caveat. Because we're looking at longer wavelengths with NICMOS, and you can only see, at the longer wavelengths with a 2.4 meter Hubble telescope, you really are only able to see the largest bars. And so when we compare the bar fraction of the largest bars at high redshift beyond, say, 0.5, compared to the present day, then the numbers are comparable. But the answer in our paper, in our letter, we found only 3 barred galaxies in the NICMOS deep field, but it was 3 out of 31, and that was the same fraction locally. So we said, well, there isn't a compelling evidence. We really don't know what's going on. So our paper challenged what Vandenberg and Abraham were doing, and there's a whole fun story for like what that led to and all the drama that happened when we published our letter, but we'll skip that for now. As soon as when we published this paper, this figure that you see on the right shows you what we consider the minimum criteria for identifying a stellar structure like a bar, that you need at least 5 point spread functions or 5 beams to identify a bar. And the curves show you how different size structures change in standard cosmology as you go back. And the number to remember for most people is that 1 arc second is roughly 8 kiloparsecs at all redshifts beyond redshift of 1. And if a bar is roughly 2.5 kiloparsecs, then you need resolution, you need 5 elements across that to be able to see that. So you can see in this plot here that we knew when the ACS camera was installed on Hubble, it would do much better than what NICMOS had been able to do. And so we would be able to tell most typical large bars after our work. Well, what happened was as soon as ACS was installed, 2 studies came out. One by Almagreen et al. And one by Jogi et al. That now claimed a result that was completely opposite of what Vandenberg and Abraham were claiming just a few years ago. These folks claimed that the bar fraction was constant out to redshift of 1, implying that there was no evolution over the last 7 billion years. But the thing to remember is that these studies, including ours and including a Vandenberg and Abraham study, were very, very small number statistics. In the Jogi et al. Sample, for example, from the GEM study, they only had 138 bars in the low redshift, in the high redshift band from 0.5 to above 0.5, and 100 galaxies less than 0.5. So with 2 bins and 2 data points, you can draw a straight line, you can draw a declining line. You don't really know what's going on. And because there are so few galaxies, you don't have consistent selection criteria. So what was really needed was a really large sample where you could really do this work carefully. And to do that, you really needed a study like Cosmos. So on the left-hand side here, I'm showing you what was the state of the art before we started the Cosmos study. This is the Hubble Ultra Deep Field, the GOOD survey, and the GEM survey. And this is what we did in the Cosmos survey. We used 590 orbits of HST to map 2 square degrees at roughly 10 hours right ascension, 0 degrees declination. And this was basically 10 times bigger than anything else that was done before. And because we used the F814W I-band filter, which is a broadband filter, we had great depth. So this survey produced a map with 2 million galaxies spreading from redshift of 0.2 to 5. And it's like having Sloan at high redshift. And the beauty of this Cosmos survey is that because it's an equatorial field, we have then followed it up in the last 15 years that we've been working on this project with data on this 2 square degree field from every telescope imaginable in the universe, well, on the planet anyway. And our team's motto is that within 9 months, we want to make all of that data publicly available. So you can access any Cosmos data for any of the data we've taken through the ursa.ipac.caltech.edu site, photometry, catalogs and spectroscopy for all of these galaxies. So that it's just been a great project to work on because it gives you the penultimate data set to study the coevolution of galaxies and large-scale structure. Now, this was an ideal data set for us to ask the question, how does the bar fraction truly vary with redshift? And then because we have such a big data set, maybe we can also start to look at what is the relationship between bars and the host galaxy disk. As I mentioned to you, there was a lot of controversy from the papers that came before, and we knew that in order to do anything at high redshift, how you select the sample is really, really critical. So we were very, very careful in how we first chose the sample from these 2 million galaxies that we had. So we chose galaxies at any given redshift that were L star and brighter, allowing for 1 magnitude of evolution that we've seen from other studies. Galaxies were just brighter as you go back because star formation rates were higher. We then cut off all of the galaxies at greater than redshift of 0.84. And the reason for that is because the F814W filter ends up sampling the rest frame ultraviolet bands when you go beyond a redshift of 0.8, and you don't want that because bars tend to disappear in the ultraviolet because there's the bomber break for stars, and stellar structures become faint, quite faint when you go into the ultraviolet. Now, you can see this by eye as well. You can look at a galaxy catalog and compare it to a visible catalog, and you'll see all the bars disappear because the data just aren't deep enough. In addition to that, we made sure that we tried very hard to only pick out galaxies that were disks. We eliminated all of elliptical galaxies. We rejected galaxies that were sort of point-like or obviously merging and disturbed. And we rejected all galaxies that might be edge-on. And in the end, in the paper, in this 2008 paper, you see we do a lot of different tests. And we believe that our sample was complete for all galaxies with half-light diameters less than 20 kiloparsecs. And it's a sample that's complete for all the data points I'm going to show you above 1 or 2, 3 times 10 to the 10th stellar masses in mass, depending on which conversion factor you choose. So when you make all these cuts, the downside of being this careful is you go from 2 million galaxies to 2,000 galaxies. But that's still great because you have 10 times as many galaxies as you had in the past. And that allows you to really do some detailed analysis, as I'll show you. So this is a fun exercise. If we were in the same room, I would ask you all to identify what you see on the left-hand side. Do you see a little sheep on the top left? And do you see a heart in the bottom left? And do you see a rabbit and maybe a mouse and a pig? And the answer is probably yes. When you look at these clouds, your brain is incredibly good at figuring out patterns. I mean, that's how we've survived as a human race. And this is how bars were identified for years. In fact, de Vaucluse at University of Texas, Austin, in his class would tell students, identify the bars in this sample of photographs. And if they didn't come back with the number that he liked, which was his number, which was 2/3 of all galaxies, he would say, oh, you're not looking hard enough. So I want you to just understand that while you can identify bars by eye, and your eye is an incredibly good machine, one should be careful of the biases that go into simply using your eyes to do that. And even here on the right-hand side, you can see, even by eye with the ACS data, you can identify things that are barred, especially when they have spiral arms coming out from the end. But we don't want to only use that technique because we recognize that our brains are wired to do pattern matching. So what we actually do is try to identify bars with more than one method and with more than one author to try to reduce our biases. The other method that we use has really been developed in the paper that Karin Menendez del Mestre and I wrote as part of our second year project at Caltech, was where we took infrared, good high quality infrared data from the 2MASS survey and really went into detail about how we can do ellipse fitting to identify bars. And we identify bars with these double signature where the ellipticity of the isophotes has to increase and then drop when those ellipses enter into the disk of the galaxy. And at the same time, the phase angle has to remain roughly constant and then change at the end. And then if you look at that paper, we identify the shortcomings. It's a good method, but it's not perfect. You get 10 or 15% false candidates. What we then did was W. Elmgreen and I used both of these methods independently to look at all 2,000 galaxies and identify the bars from that sample. And this was the result. So what I'm showing you here on the x-axis is look back time as a function of time. And each bin here is going back 1 billion years back in time. So 2, 3, 4, 5, 6, and 7 billion years back. On the top, I'm showing you the results when we classify the sample with visual classification. And the bottom, I'm showing you the data when you classify them using that automated ellipse fitting and position angle classification system. Like I said, both Debbie and I did this separately, and we reconciled results when we disagreed, which was in like less than 5% of the cases. On the y-axis here, I'm showing you the total bar fraction. So that's the total number of galaxies that are considered barred divided by the total number of disk galaxies. Our sample is all disk galaxies. So that's the sample, the number of galaxies in that bin that we're able to classify. And the error bars are just Poisson distribution. They're really primarily driven by number statistics. And what you find is this amazing trend where the bar fraction is declining by a factor of 3 as you go from the present day universe to 7 billion years ago. Whereas today, 2/3 of all disk galaxies are barred. 7 billion years ago, only 20% of the disk galaxies had a bar. And the evolution was kind of monotonic. What this tells you is that the universe was a very different place 7 billion years ago, that only 1/3 of the disks were mature in the same way that the 2/3 of the disks are mature at the time. And in every case, we find this significant decline in the bar fraction. So when I send this image to Bob Abraham, whose work I had challenged before with the NCMOS Hubble Deep Field, and he was a co-author, and so were the Elmagreens, were also a co-author on our paper. He said, oh, he almost fell off his chair and his socks were knocked off because it was such a stunning result. It took us 2 years to do this work because I had Bob and Bruce and Debbie on my team who are highly skeptical and had learned from the controversy we had. So if you go through the paper, we really look at this work in great detail and look at every selection effect that could give you this trend. And every selection effect will give you a declining bar fraction as you go back in time. So we take into account every single one of them using Sloan data and doing simulations to make sure that we're not being biased here. So I will argue that this sample and this study is one of the most robust studies. How does it compare to what was done previously? In red here, I show you the 2 points from the Abraham sample, and we added the error bars and redid their analysis. The 2 green points, or the 2 sets of green points are Jogi et al. And this purple point, and this purple point is the first Elmagreen study that claimed a constant bar fraction, and this is their new paper with 2017. And what you find is something amazing. One of the things I forgot to tell you is these are all the bars, and these are the strong bars. That's the difference between these 2 panels. So when we do visual classification, all the bars are things that are oval and rectangular. Strong bars are only the rectangular. In ellipticity and position angle classification, we require an ellipticity threshold for the strong bars and for the strong bars here, and no such criterion for the weak bars as well. So what we find here is when we look at the strong bar evolution or the weak bar evolution, we find that factor of 3 decline. And amazingly, the Abraham points fall right on that trend. And so I always say, either they're brilliant, that just with 30 galaxies, they knew the right answer, or they were lucky, or both. But they had the right answer, even in the Hubble Deep Field. And now what our data is able to show you is precisely how that is happening as you go back in 1 billion year chunks. What's interesting also is that in fact, in the Jogi data, they also had a decline. And in the Elmagreen data, they also have the same trend. So everybody really, all the data are really consistent with each other. The only reason the Jogi data points are higher is because they are using a magnitude limited cut, which means they're looking at more massive galaxies, and that gives them that offset, as I'll explain. But the most satisfying thing about our work is that so many different studies that have come after us, both observational and theoretical, have confirmed this result. In the Kralchik work, for example, they started with no assumptions, and they're able to see the same trend. So this was very satisfying to me, having worked on it for many years, that our result was really showing something that was quite robust scientifically. Okay, so the main conclusions here are the overall bar fraction declines by a factor of 3. We can look at this evolution in bins of 1 billion years, And this now places strong constraints on the assembly and evolution of disks. But you might ask, why is this happening? Why are we seeing this trend? What is going on in the universe? And to answer that question, we now try to look at the bar fraction as a function of galaxy properties. And I'm only going to show you one property, but in the paper, we have multiple properties that we look at. Now what I'm showing you is the same thing, the bar fraction on the y-axis, but on the x-axis, I'm showing you the stellar mass that we calculate from our photometric SCDs. The red curve here shows you the galaxy population as it was in the bin from redshift of 0.6 to 0.84. This shows you the population of galaxies that we consider 4 billion years ago. And this shows you the population of galaxies 2 billion years ago. Let's just look at the highest mass bin. What's amazing here is in the highest mass bin, 7 billion years ago, the most massive galaxies were already barred at a 50% rate. And they've only evolved slightly. And the majority of the evolution is really happening in these low mass systems. It's the low mass systems that are slowly acquiring their bars over the last 7 billion years. And that's why we see today, all galaxies more massive than 10 to the 10, roughly have a bar fraction that is the present day fraction of 66%. It's not as if galaxies simply move straight up, obviously, as they acquire more mass and evolve, they probably go towards the right here. But the main trend here, the main takeaway is the most massive galaxies were already barred at the same rate as they are today, 7 billion years ago, and the least massive galaxies had the most evolution over the last 7 billion years ago. When we compare that to the size of the bulge or the color of the galaxies, we see the same pattern. So to us, what this means is that the early type galaxies, the galaxies that are the most massive, that are the most bulge dominated, that are the reddest, really were in place 7 billion years ago. And majority of the evolution has been happening in lower and lower mass galaxies. We're really seeing downsizing, the same downsizing that we see in star formation, we see in galactic structure. The most massive things formed first, and the least massive things formed last. So our conclusion here is that if you were to look at the Hubble sequence, we ignore the left-hand side of this sequence because we're not looking at elliptical galaxies, but other studies show that they likely came in place maybe earlier than redshift of 3. The middle part of the Hubble sequence really formed between redshifts of 1 and 3 when the disks were first formed. And they were done with their evolution. They became quite boring in some sense by the time we got to Z of 1. And most of the action in galaxy evolution is really happening in the late type galaxies at Z less than 1. And it's happening, as a mass dependent evolution. So what about bars in the local universe? Like we're now stuck in a quarantine and we can't go out, but just wanted to put up a picture of a bar because I'm sure we all miss that. And I'm going to talk a little bit about bars in the local universe, because if this is the case, we should see whether this evolution is happening today. And do we have any evidence of that? So to do that work, we really use a survey called S4G. We want to ask the question, what is the precise local bar fraction? And do we see evidence of such evolution? So this is the survey that I'm the PI of. It's two of the largest surveys that we did with Spitzer called S4G. We spent about 830 hours, and it's the largest, deepest survey in mid-IR wavelengths of galaxies now and in the foreseeable future. So I highly encourage you to look at this data set, but that is also freely available along with all of our enhanced products on Ursa. Because nearby galaxies are the fossil records of all galaxy evolution, having such a survey that is incredibly deep, our azimutally averaged 3.6 micron AB magnitude limit is 27.1, which means we're looking at the outskirts of disks with a stellar surface density less than 1 solar mass per square parsec. I mean, just, in a place where gas dominates effectively, and we have beautiful, detailed structural information on all 3,000 galaxies in the nearby universe. So any simulation or a test you do that says, let me try to reproduce the universe today, it has to match what S4G sees. So I would like to advertise this as as a sample, which you can use for a variety of different uses when you're trying to understand stellar structure and mass in the local universe. The way we pick the galaxies for S4G is we pick them that were nearby, less than 40 megaparsec, chosen not on an infrared criteria, but a blue band criteria, that the disks had to be big so that we could see structures inside of them, and they had to avoid the galactic equator so that we're not confused by foreground stars. When we did this survey, we realized we missed a lot of elliptical galaxies because of our reliance on a velocity that was measured by radio observation. So we went back and we did S4G plus, and with roughly 200 more hours, we filled the sample with early type galaxies or elliptical galaxies as well. We spent 4 minutes per pixel, and Spitzer was so sensitive. Like I said, you get to 27 magnitudes per square arc second at 3.6 micron, which is incredible. We go down to very, very faint stellar structure in these disks. It's a huge team. I was the PI, and then we had a lot of people from around the country and the world responsible for various parts of this. And I think we had a student also at UNAM who worked on some of this with me and missing the name of my collaborator in Marseille. Anyway, it'll come back to me. Leah Tanasula. So anyway, like I said, all of this data is available to you. And we want to ask this question: what is the precise local bar fraction? We know that majority of the studies have shown that 2/3 of all local disk galaxies are barred. Some studies say, oh no, it's 25 or 40%. Some are reasonable because they use a different definition of a bar. Some are completely delusional. So I just wanted to caution you against blindly using numbers in the literature because they are affected by so many different things. And what we try to do in our work is to try to use the same technique for identifying a bar and choosing the sample so that we are comparing apples to apples, no matter what redshift bin we are in or what wavelength we're in, etc. So with the S4G data, this is the beautiful data from Spitzer. All of this is available to you so you can do this work. And I just want to show you one result. Okay, so this is my last point from my talk. What I'm showing you now is from the S4G survey, roughly 1,500 galaxies, and I'm showing you the bar fraction again on the y-axis, and again stellar mass on the x-axis. And what you see here are strong, all the bars are on the top, the strong bars are with the diamonds. We identified them using two techniques, the same way we did this for the Cosmos data, for the 2-mass data. And what we find is something amazing. Above a mass of 10 to the 9.2, the bar fraction is 2/3 for all the bars, or 1/3 for the strong bars. And we see this sharp decline right where the galaxies are of the same mass of Magellanic types. And what this means is that we are seeing the same trend that we saw at high redshift. So at high redshift, at high redshift, what we saw was that the most massive galaxies above a mass of 10 to the 11 had about half of their disks had barred by redshift of 0.7. About half of the galaxies with masses of 10 to the 10.5 had bars in them by a redshift of 0.5. About half of the galaxies with disk masses greater than 10 to the 10 had bars by redshift of 0.3. And today, we come down, that mass limit has moved down to 9.2. And so today, the majority of the evolution in disks acquiring bars is happening at a mass of 9.2, and there's very little happening beyond that. The evolution is much slower for the more massive galaxies. So in conclusion, what I'll say is we have learned that the total bar fraction is not constant, and it's not binary, but it's declining, and it declines monotonically over the last 7 billion years. All of the data, all of the studies are now consistent, and people have repeated this experiment multiple times. Webb will push this further, as I'll show you in a second. We have also found, because of the large sample from Cosmos and the amazing amount of multi-wavelength data, that we can also see why this decline is happening, or what is the decline correlated with. And the decline is correlated with stellar mass, color, and bulge domination. We're seeing downsizing. In a paper that I'm not going to show you, but I'm happy to, if you look at the 2012 paper we published, we show that in galaxies that are dispersion dominated or dynamically hot, we don't see bars. So one clue as to why some galaxies that are massive enough don't have bars is because they're dynamically hot. We can tell that from when we study their disordered motions to their ordered motions. Another possibility that galaxies don't have a bar is because they might be gas rich. And if they're gas rich, simulations show that gas, like dark matter halo, retards or slows down the formation of a bar. So both the detailed analysis of how the dark matter plays a role in the evolution of the galaxy disk, how the gas and the gaseous disk prevents the transfer of angular momentum, are really details that we haven't figured out as to exactly which galaxy, why some galaxies don't have a bar in them. But we right now know in terms of the physics that the physics is still the same, that if galaxies are dynamically hot or they're too gaseous or they're still being dominated by a dark matter halo, they're unlikely to have a bar in them. We see today at the local universe that the bar fraction is declining sharply at masses less than 9.2. It's consistent with what we see at high redshift. The bar structure is consistent with theoretical models, and I encourage you to see the 2 papers by Thay and Kim that we worked on, which talks about how bars grow over time. And just a warning to, if people are interested in studying bars, is that, one must really try to take great care in consistency. Otherwise you end up in that 10 years of uncertainty because people are defining things differently and you have apples to oranges comparison and inadequate sample size or inadequate completeness criteria. We still need to figure out how do bars vary with gas properties. ALMA is going to be really good for that. How do bars influence AGN and star formation activity? We've done some work on that with Mauricio Cisternas and R.L. Yarber. And is there a ceiling on the bar fraction? Why will the bar fraction eventually get to 100%? And if not, why? So those are outstanding questions. And just one last thought here with James Webb, which we will launch next year. So with James Webb Space Telescope, we will be able to see at 2 microns, where it's diffraction limited, 5 PSFs corresponds to roughly 0.32 arc seconds. Or in other words, we should be able to identify any structures with a semi-major axis of 1.2 kiloparsecs and larger over all redshift range. So we should be able to repeat this work with Webb data and push the work out to redshift of 3 or 4. Now, the hard part here compared to Hubble or W1st, aka Roman telescope, is that Webb is not a survey telescope. So, that's the trade-off that we make. So this might be hard work. And the other selection criteria we have to worry about as we go beyond redshift of 0.8 is the merger fraction, and gaseous fraction in the universe will also increase, and the galaxies are likely to be smaller. So it's unclear to me how well we will be able to do, but that's the next step we need to take. So I'll stop there and take questions. I hope I've convinced you that we've kind of pieced together the jigsaw puzzle here and shown how galaxy disks came into existence.
Okay, thanks the speaker. Questions, comments, suggestions? Raise your hand, please.
I think somebody has a raised
Jorge Barrera, go ahead, Jorge.
Thank you, Nisim. Thanks, Kartik. Really, really great presentation. I was wondering about, we have been doing some work regarding the kinematics, the impact of the bars in the kinematics of galaxies, of the galaxies with Khalifa. Have you tried to see what is the impact in kinematics with the S4G galaxies? Because as you mentioned, there is we expect that the bars impact the star formation or the AEGIS in the central region. Thank you.
Yeah, I know, it's a great questions, and I'm hoping that with Megara we will be able to do all of the S4G galaxies. I'm hoping Armando and his team will get really good spectroscopic IFU maps for all of these galaxies. Some of the things that I didn't get to cover here is when I started studying bars, I thought, oh, bars are the most important drivers for change in galaxy today. But it turns out, even if they do it, it's really difficult to see them having a whole lot of impact. So one thing we've done in a paper that I published in 2005, I think, is we did show that barred galaxies that bars are primarily responsible for driving circumnuclear star formation. So we do see an increase in central star formation whenever bars are present. The interesting thing, though, in that study was that was true for early type galaxies, but not true for late type galaxies. And we have a couple of ideas in that paper about why that might be. It might be a pattern matching thing between the bar pattern speed and the spiral arm pattern speed that allows a pipeline of gas to form to allow the gas to come in. And so star formation is sporadic in early type galaxies compared to late type galaxies. The other thing that we found was interesting was there's a paper by Munoz Mateos in 2012, I think, in 2013, where we looked at how the bar impacts the profiles of disks. How does it change the profile, and does it flatten, or does it change the profile? Is there a break at the end? Does it lead to type 1, type 2, type 3 disks? And we do find that the bars do play a role, but really it's a combination of the bar plus the spiral arm that plays a much bigger role in redistributing the stars. But again, the result is it's very difficult work to do and hard.
Yes.
And then in terms of chemical evolution, Patricia Sanchez Blasquez and her team have found that, in fact, they don't see the bars doing much in terms of redistributing, changing the chemical abundance gradient. And the initial results from Zaritsky et al. Were spurious. And with the data that from Khalifa et al. Show that really we don't see that impact because I think the bars are just not having the impact that we thought they were. And in a different study that I did with my students, we found that we don't see a very strong correlation between bars and the central black hole activity. And we don't see a strong evidence of bars and disk star formation.
Yes, so that's one of the things that we found in this 2014 paper, and with Khalifa data is that we don't seem to find any strong, distortions especially in the ionized gas kinematics, the ionized gas velocity field, when you have a bar. So if you compare a sample with bars and no bars of disk, you don't seem to find any strong distortion in the velocity field that you will expect to see from simulation, for example, from Leah, that she shows that depending on the angle of the bar and the disk, you may expect to find this wiggle of the velocity field due to the bar. But with the Khalifa resolution and for the ionized gas, we couldn't find anything. And it was even, let's say, worse for the stellar velocity field. So what we found is that regardless if you have a bar or a plain disk, you don't seem to find any strong difference or any strong impact of the bar. And I was wondering, maybe with a higher spectral or spatial resolution like MUSE, you may find some of these disturbances caused by the bar, and especially in the ionized gas kinematics.
Yeah, I mean, if you look at a paper by Regan et al. From 1999, there's a Fabry-Perot, very high resolution, spectral resolution and spatial resolution data from the Magellan telescopes for NGC 1530. You see very, very sharp shock signatures.
Yes.
But you see
Also,
that shock is over 100.
PATI 2005, they also find this wiggle.
Yeah.
So, but with a large sample of 80 galaxies, we couldn't find any. But
Yeah,
maybe it's because of that.
I think the shock is very, very narrow. It's only over 100 parsecs. So I have all my data, which I didn't put in this talk, where I can see in NGC 1097, the shock where the gas is just so narrow. So you need really, really high spatial resolution and spectral resolution to see it. And it might be that with Khalifa, the resolution is just not good enough to see it.
Great, thank you.
Yep. Do you want me to call on people? Aida and Octavio have their hands up. Nassim?
Yes, so I think Octavio is, please go ahead.
Go ahead, Octavio.
Okay, it's a little bit following Jorge's question. You mentioned, as people already know, that gas fraction also can weak or destroy the bars. People have known that in simulations, but typically simulations were with a isothermal equation of state for gas, so artificially they over-destroy bars. You probably know that even state-of-the-art galaxy formation simulations, they have a lack of healthy bars. And the only successful cases like Auriga project or FIRE, they have excessive even AGN or starburst, nuclear starburst. I wonder if you have correlated as a function of redshift, how frequent those bars, if you have an increase of nuclear starbursts or AGNs, because that would be a very nice constraint for galaxy formation simulation, because this is an open situation from the point of view of simulations.
Yeah, and so let me first just make a comment that I don't believe that once a bar is formed, you can destroy it very easily. The only way to destroy it is with what I would call a major merger. You would really need an equivalent size galaxy to come run into it. But it is possible that excessive gas may delay the formation of a bar. And so I think those are things that we need to keep separate. As a function of redshift, we said, look, today, most of the AGN are in elliptical galaxies, 15 to 20% of them seem to have an AGN. As we go back in time, we know the AGN fraction is increasing, but the bar fraction is decreasing. So if bars are playing a role in funneling gas to the center and triggering an AGN, we should be able to find that signature. We should be able to find these two opposite trends cross. And we were not able to find any evidence of bar playing a role in enhancing AGN activity. So this is the work by Mauricio Cisternas et al. And what we found is that there was a tiny signature in present day with strong bars driving gas to the center and triggering an AGN. But as we went back in time, the AGN fraction, and I say AGN fraction simply because we're using X-rays as a proxy for AGN activity. The AGN fraction in barred and unbarred spirals was the same. And initially you find a difference if you don't account for the changing mass in your sample size, because bars are more present in more massive galaxies, and AGN activity is more common in more massive galaxies. You find a correlation, but as soon as you take that into account, it disappears. So what we concluded in that paper was that other instabilities, like spiral arms and bars or collisions between giant molecular associations, are probably more effective at triggering central activity. In this case, I'm just saying central activity because it's central X-ray emission, rather than bars themselves playing a role. So I think bars are really good at transporting gas to the central kiloparsec, but after that, I don't think they play much of a role. I really don't. I mean, even though there are some examples of good, double bars, we've never been able to show that a bar within a bar, like Schlossman et al. Showed in their theoretical paper, is an effective way of driving gas to the AGN in the center. In terms of star formation, we haven't done that. Maybe with JWST, we should do that, because then we will really be able to isolate nuclear star formation. And maybe we can do it with like Paschen alpha, because the dust emission will be so much that we will need something like that to identify the nuclear star formation, which we haven't been able to do so far. Maybe with ALMA we can do it, but I haven't thought about it yet.
Okay, thank you. That means that people in galaxy formation simulation has to keep working on the IS-10 physics.
Yeah.
Okay,
I'm happy to work with anybody on ALMA proposals. It's one of the things I can do without any conflicts as a NASA person.
Okay, thanks.
Okay, I think last question. Aida, go ahead.
Hi, Kartik. Thank you for a very nice talk. I actually have two questions, but I'll ask the first one. So how come when you use this ellipticity plus position angle method for finding the bars, you systematically lose bars? You don't find more, you systematically lose bars. So is there, do you understand why that is?
You mean compared to a visual classification?
Yeah, compared to a visual classification.
Yeah, I think, so yeah, in Kareem's paper, there are 4 or 5 reasons why that happens. I'll just give you the most obvious ones. For example, imagine that the bar and the disk position angle are the same. And then you will not see the phase angle change that you expect to see. So if the bar was like this and the disk was like this, you would see a sharp jump, and then you don't see that. So automatically classifying it, you will say there is no bar. So that's one reason. Another reason is in many of these bars, we see the spiral arms like do this very, very slowly. And when that happens, you don't find that nice sharp drop in ellipticity. And so that's another reason why we sometimes are unable to classify that bar convincingly. So what we've been doing with S4G is when things are ambiguous, we will go back and try to reclassify them. But to keep things clean, if something fails our position angle ellipticity classification criteria, we don't include it as a barred galaxy. So it statistically is always lower than what your eye can do, because it can pick up those strangeness. And then when the data are ratty, it's really difficult, right? Because you're trying to put isopods, and if you don't have clean subtraction of stars in the foreground, then the algorithm can fail. So it's a little bit more work.
Okay, thank you. Can I ask my second question, Nisim? Or is...
We're going till 2 o'clock, right?
I don't know.
Okay, it's fine. I can ask it later. Don't worry.
It's another question from Hector.
I think we have time. So it's 53. So we can still have 5 more minutes of questions if you want to ask it, Aida.
It's yeah. So M83 has a circumnuclear cluster.
Yeah.
Is that considered a bar? I mean,
so the
or it's not?
the M83, the primary bar in M83 is large, right? It's like 5 megaparsecs away, and that bar is so prominent. So do you mean, is there another bar inside of the central kiloparsec or so?
Yeah, like within I don't know, 200 parsecs of the center, where the spiral arms are starting to.
Yeah, I have no idea. If you look at my 2001 paper and you look at figure 7, I know it's like what I did was I took some MICMOS data and I artificially smoothed the central region of NGC 5383 with a half arc second kernel and a 1 arc second kernel. And because when we're looking at optical data and there's dust, and if you start smoothing it, you can produce a fake bar, you can produce a fake ring. So I think that identifying nuclear structures is just very difficult. And the best way to do it is through kinematics of the molecular gas. Okay. So I would warn people against using morphology in the nuclear region and inferring anything about what's going on in terms of the dynamics. I think that can be really problematic.
Thank you.
Yeah. Hector?
Okay, Hector, go ahead. Last question.
Yes, last question. Let's think that gas content indeed impacts the properties we see for bars today. So my question is for you, how do you expect to check that effect on the properties that you see in bars today, considering that you have only a photometric sample?
Yeah. So let me step back for a second and say both dark matter halo and gas content impede or prevent the formation of a bar at the beginning of when we say time equals 0. As gas gets consumed, or as the dark matter exchanges angular momentum with the baryons, the bar eventually does form. It's just slowing it down. So I think we have to be careful comparing the current gas content and saying, well, that must mean something about the evolutionary history of whether this galaxy got a bar or not. What we really need to do is to look at a sample of galaxies and look at their gas properties at redshift when they first were starting to form bars at redshift of 3 or 4, and then ask the question, as we go forward, are the galaxies that are predominantly more barred, less gaseous, have used up their gas? And I think that's going to be a difficult sample for us to collect because we have to collect gas measurements over redshift space. So if you just did it locally, like let's say we used LMT or the 12 meter at NRAO, or what used to be the NRAO 12 meter, and collected single dish data, and you simply plotted what is the bar frequency in galaxies as a function of their gas content. And let's just say molecular gas content, because we don't care about the H1 because it's in the outskirts and the bars only form in the center. My naive assumption would be that you would expect there to be fewer bars in galaxies that are more gas rich. generically, that's a true statement because more gas-rich galaxies are also late-type galaxies and bars formed last in them. So it's difficult to correlate whether the bar is absent in them because there was more gas there, or because the disk was less massive, or it's just a mass-dependent evolution. So I think it's really difficult to tease it out. So it's easy to do for somebody like Leah in her simulations, but I think it's hard for us as observers to really tease out the right answer. Does that make sense?
Yeah. Just one last final comment. What if instead of few bars, we would say shorter bars?
Yeah, that'd be interesting to do. So if you look at the Kim et al. Papers, one of the things we were trying to show is that bars that formed first in the history of the universe should grow over time, because as the bars exchange angular momentum and energy, they should become more rectangular and get longer. We have seen that both in observations, and we've now shown that observationally as well with the work that Tayan did with S4G. So I think you will see that bars in late type galaxies, more gaseous galaxies, are shorter. But I can't tell you that they're shorter because they just haven't had time to evolve to be longer, or they're shorter because of some other reason.
Yeah, right.
So it's hard to decouple all these because there are just too many correlated factors going in. So we'd have to think about setting up that experiment more carefully.
Thank you.
Yeah.
Okay, thanks. Kartik again.
You're welcome. Thank you for the invitation. I hope you all stay safe
it's a
out
pleasure.
there.
Gillian, if someone wants to say goodbye, turn on the mic.
Thank you, Kartik. This was super interesting.
You're welcome. Maybe you'll
Thanks for
become an
coming.
extragalactic astronomer now.
No. But I'm glad that there was time to have lots of questions and everybody could participate. So thanks everybody for being here. And thanks, Kartik.
You're welcome. Okay, have a good day, everybody.
You too. Bye-bye.
Bye. Thank you.
Bye.
Thank you, Gillian.